So you've probably guessed by this point that the reason that the real state of the atmosphere, one of the reasons the real state of the atmosphere doesn't look like radiative equilibrium is that it turns out the radiative equilibrium state of the troposphere is unstable to convection. It has entropy decreasing with height. And so it convects. And that's particularly true in the tropics, but it's even true in the mean state of the troposphere. And one simple way to account for this in a simple model of the vertical profile of temperature in the atmosphere is to do something quite simple. Wherever the entropy gradient is negative, set it back to 0. That's what convection does. Set it back to 0 in such a way that the total energy of the column is conserved. And that state, in which all the negative profiles have been removed and replaced by 0 gradient, is called the radiative convective equilibrium state. Actually, this term is much more general. It simply means the state in which the fluid is statistically in equilibrium with both radiation and convection transporting energy in the vertical. Now, convection, even in a pan of boiling water, but certainly in the atmosphere, is a chaotic process. It's random in space and time, fairly random. And so when we talk about radiative convective equilibrium, we're talking about a statistical equilibrium state. In fact, convection is chaotic. The fluid is always moving. It's turbulent. But if we average over time and or space, the statistics of the average state can be very stable. And we call that average statistical state the radiative convective equilibrium state. And we're going to say a lot more about that as we go forward. So what does this look like? Well, you've seen this curve before. This is an early calculation of pure radiative equilibrium done in the 1960s and making an important assumption about the vertical profile of water vapor in the atmosphere. That was held fixed for this calculation. As we'll see, that's not a proper thing to do because, in fact, it's the convection that determines the vertical profile of water vapor in these states. But for the purposes of this calculation, the water vapor was fixed. We noted that it was too hot at the surface. It was 333 degrees Kelvin. This is supposed to be a tropical mean state. And too cold at the tropopause, down around 180 degrees, where what we observe is closer to 200 or even warmer than that. Now, when we apply this adjustment so that the entropy profile is always neutral, where it wants to be negative, we get this adjusted state, which is called the dry adiabatic adjusted state. We'll see in a minute why it's called that. It's cooler at the surface. The surface temperature is dropped down to about 317 degrees Kelvin, which is still way hotter than observed in the tropics, but a lot better than 333. The tropopause is higher and warmer, and there are even some differences in the stratosphere. Now, why would the stratosphere be different, given that there's no convection going on in the stratosphere? And that reminds us that radiative transfer is non-local. Whenever you change the temperature or emissivity of any part of the atmosphere, potentially it can affect the temperature of all the other parts of the atmosphere. And that indeed happens. The photons coming up from the troposphere are different in this different state, and so the stratosphere adjusts to a slightly different profile. So although that's better, it didn't solve all of our problems. The radiative convective equilibrium state that we're calculating is much closer to the observed tropical atmosphere than pure radiative equilibrium, but it's still too hot at the surface and still a little bit too cold at the tropopause. So it turns out that we're missing something else, and that is the fact that in the real world, these ascending currents of air carry water vapor that condenses. And when it condenses, it releases into the air the latent heat of vaporization, and if the water freezes, also the latent heat of fusion. And so the process of convection is no longer adiabatic, at least not adiabatic by the way we formally defined it. This is a photograph taken from an airplane of the tropical atmosphere, showing a sort of a typical state that you might find it in. And you see clouds. When you look at a cloud, what you're seeing is a collection of very small water droplets that are, or ice crystals, which are in suspension. And these are cumulus clouds. They're the visual signature of updrafts, mostly updrafts, in what we call moist convection, where water is condensing. There's a whole spectrum of them in this photograph, ranging from very shallow, tiny cumulus clouds up to trade cumulus or cumulus mediocris, all the way up to cumulonimbus clouds, which are strongly precipitating and can extend all the way up to the tropopause. So we have this whole spectrum of clouds. But the phase change of water inside the clouds really changes everything and leads to a quite different state of the troposphere than we would see in dry convection. So somehow, if we want to get a better estimate of the vertical temperature profile and other characteristics of especially the tropical atmosphere, we have to account for the phase change of water. So we're going to talk a little bit about that.